Hello, I am Shuyok Chaba. I am a software developer from Brunswick, Germany, and this lesson is for week 1 of Introduction to Music Production at Coursera.org. I will be teaching the fundamental ways to visualize sound. As with any working environment, you need a way to visualize the data you are working with, and in this case we are working with sound, so the data we need to visually represent is the audio data. The three main ways to visualize sound in our DAW is the oscilloscope, the spectral analyzer, and the sonogram analysis. These basically all show function graphs the same way you learn in mathematics or physics classes. The difference between them is only what it is you are viewing on the X and Y axis. What we are interested in when viewing the sound, so to speak, are amplitude, frequency, timbre, and how these things change over time. For this presentation, I have generated with MATLAB a few audio samples just to show the differences. I am using Sony SoundForge to show the views, and although Sony SoundForge is not fully capable DAW, it will do for the purposes of this presentation. Now, as you can see the samples here, I have created just a simple 440 Hz A sound sine wave, and to present, here's the first main viewing method, the oscilloscope. As you can see, the most basic and the most simple, the most often found. On the x-axis you can see time passing, and on the y-axis you can see the amplitude. Now, next to this simple A sine wave, I have also generated a few extras to show you the differences, what happens when one of these properties that I have mentioned change. So changes in the amplitude would mean that on the y-axis we get smaller waves. Changes in frequency will change the wavelength, so one full sine wave will take less or more time on the x-axis. And changes in timbre will keep the amplitude and the frequency somewhat constant, and it will just change the shape, the image of the wave over a wavelength. Now, the second type of view is the spectrum analyzer. This exists because frequency can't really be determined on an oscilloscope, especially when you zoom out enough to see maybe multiple seconds. So this is the oscilloscope view. Here on the x-axis you can see frequency, and on the y-axis you can see amplitude. Now, changes in amplitude will again show up on the y-axis. As you can see, it gets smaller when I lower the amplitude. Changes in frequency will show up on the x-axis. This is pushing up that A with 1 octave. And changes in timbre will add or remove new peaks, which will all be at integer multiples from the fundamental frequency, and these partials make us hear the difference between different instruments. The problem with this one is that it shows us a snapshot in time, so we don't see how they change over time. And for this, to see over time what changes, the sonogram analysis is the simplest. In this case, on the x-axis we see time again, on the y-axis we see frequency, and on the z-axis, so to speak, the color change would mean change in amplitude. So x-axis time, y-axis frequency, and color change means change in amplitude. So here we see a red bar at the 440 Hz mark, and if I change the amplitude, you will see that the color of the same bar will change, but nothing else. If I change the frequency, then the original wave will move up on the vertical axis, and we can see at the 880 Hz mark the same thing. And changes in timbre will again add or remove horizontal lines, again all integer multiples of the fundamental frequency. So recording went pretty well for this presentation, and I used the lavalier microphone and Sony SoundForge snapshots, and I hope I got all my points across. I'd love to know what you think of the recording and the material. Thank you for watching.